Thank you for organizing the conference and inviting me and letting me speak. So this is joint work with my co-authors Andrei Grezhik and Dan Krall, the speaker from the plenary talk this morning. So the basic outline of the talk will be I'll give some background from kind of classical graph theory problems and how they relate to this, to the conjecture that we looked at. I'll quickly recap graphons, but we've had 2 talks already that went into them. And then I'll say the statement of our results, maybe say a few words about the proof, and give a conclusion. So I'll start first with some problems kind of without mentioning graphons, because these are kind of classical graph theory, extremal graph theory problems that were studied before the whole theory of graph limits. So the first question that I'll review is, so given a graph H, suppose we have a graph that doesn't have any copies of H, how many edges can this graph have? So the very well-known result that probably everyone knew in undergrad or high school is if this H is a triangle, so you have a triangle-free graph, then the maximal possible number of edges you can have is n squared over 4. And in fact, we can also say that if you have equality, if you have exactly n squared over 4 edges, then your graph must be a complete bipartite graph with equal sides, with equal sizes of sides. And well-known result of Turan generalizes this to cliques instead of triangles. So if you have a clique of size t, then the best you can do is take t minus 1 equal parts and take a complete multipartite graph between them. And for general H, this is also true, at least asymptotically, due to Erdős, Stone, Simonovic. So the answer depends on the chromatic number of H, but the construction is the same thing as you get for the clique, with the chromatic number with T being replaced by the chromatic number. And asymptotically, again, if you have a sharp bound, then you must asymptotically be this complete multipartite graph. So for this problem, the solution, if you have this graph H, the solution to the problem has asymptotically a unique structure. So here it's maybe bipartite or 4-partite or t-partite, t minus 1, but it's unique. So let's look at another problem. So suppose we now fix the edge density and we look at what's the possible triangle densities, and let's just look at what's the minimal possible triangle density. So the edge density is some p. If p is at most 1/2, then obviously it's 0, but if p is greater than 1/2, it's not obvious. In fact, this was solved by Razborov using the flag algebra method, which Dan mentioned this morning. And the optimum comes from taking a complete multipartite graph with k kind of a bunch of equal parts and one remainder part that's smaller, possibly. And you can convince yourself that among these graphs, there's going to be a unique one with the right edge density, and that will give the minimal triangle count. So this was extended to larger clique sizes by Nikiforov and Reiher. But the other result I want to mention is that here it's actually not going to be unique. So a paper by Pikurko and Razborov determines what the extremal graphs are for this problem, what the solutions are for this problem. And so here we have this. So this is the graph I mentioned where you have a complete multipartite graph with a bunch of equal parts and then one smaller one left over. But you could take 2 of the parts and you can replace it with any triangle-free graph with the same edge count. So here, maybe it's not obvious, this is not complete. This has fewer edges so that the number of edges here is the same as the number of edges here. And then this will have the same triangle count. So here, the answer is not unique to this problem, but we can add another condition to it, and then it will be unique. So exercise, if you add the condition that the induced density, D is the induced density of the co-cherry is 0, then it must be complete multipartite, and then you must have this graph. Okay, finally, let's look at a third kind of quick problem. So given a graph, what is the minimum of the triangle count plus the empty triple count? So it's not hard to convince, so the answer is 1/4, and there are many extremal cases. In particular, the extremal cases are the n-half regular graphs. So we could have a complete bipartite graph, we could have 2 cliques, or we could have kind of a 1/2 random graph, Erdős-Rényi random graph, which will be also sharp asymptotically. So again, there are many extremal cases, but we can, again, add conditions to make it unique. So if we fix triangle counts to be 0, then we get the complete bipartite graph. If we fix the empty triangle to be 0, then we get the 2 cliques. Or if we fix the homomorphism count, which can be expressed in terms of the induced counts to be 1/16, then, as was mentioned, then that forces the structure, at least, to look like a random 1/2 graph, which isn't a single graph, but if the number of vertices is large, then 1/2 random graphs look similar. Okay, so let me now quickly recap graphons. I'll go quickly because we've already had 2 talks on this. So the definition of a graphon is you have this function from some probability space, which for our purposes we can take to be 0, 1 squared to 0, 1, which is measurable and symmetric. And you can think of these as the limits of dense graph sequences. So in particular, the number of edges kind of grows with the number of vertices squared. And for any k, W generates a random graph of order k, which is kind of the analog of, for a graphon, if you have a graph, you can take k random vertices, and this is the analog of doing that for a graphon. And sure enough, there are many equivalent, the nice thing about the dense graph theory, graph limits theory, is there are many equivalent notions of convergence, but one of these equivalent notions is that for any graph H, this density of the sequence converges to the density of W, of the graph in W. And then these extremal problems in this language have very nice solutions. So this first problem, if you have a graph H and W has no copies of H, what's the maximal possible edge density of W? And by Erdős-Stone-Simonovic, the answer is chi-H minus 2 over chi-H minus 1. And then it has a unique solution. So Dan alluded to this notion of weakly isomorphic, which I don't want to define, but it has a nice definition and many equivalent characterizations again. And basically any solution is essentially equivalent to this complete multipartite graphon with the proper size, depending on chi of H. So in this language, this question for any H has a unique solution. So now if we look at the triangle count with the minimal triangle count with the fixed edge count, then the Rasborough and the Pikurko-Rasborough result kind of says that it's not going to be, it says that this graphon gives the optimal solution, but again, we can replace this part here with any triangle-free subgraphon that has the same density. So it could be this graphon, or it could be this graphon where this kind of is a lower density. These are not necessarily drawn to scale, but I wanted to illustrate what can happen. So it's not unique, but if you add another condition, then it is unique. So finally, for this problem, what is the minimum of the triangle plus empty triple count in a graphon? The answer is 1/4, but many graphons minimize it. Any graphon where each row integral is 1/2 will minimize this problem. So you could have any of these graphons minimizing it, but you can again add a condition and then make it unique. So if you can add that the triangle density is 0 and then you get the first one, the empty triangle density is 0, you get the second one, or for example, the home C4 count, you can fix that and you get this third one. So the question we studied is, does this happen in general? So the precise statement of the conjecture, and this was conjectured by Lovász Sr. and Lovász Sr. and Szegedi, is so given a finite set of graphs, h1, h2, hk, and a finite set of density constraints, delta 1, delta 2, delta k, the conjecture said that if there exists a graphon W such that it satisfies these density constraints, then there exists a finitely forcible such graphon, which is equivalent to saying that if you have this finite set of constraints, you can add a finite further set of constraints, and then your solution is unique. And so Dan talked about this a bit. Earlier I was talking about extremal problems. Here it's fixed densities, but the two conjectures would be equivalent. So this is equivalent to saying that any such extremal problem has a finitely forcible solution. So I guess the punchline has already been said by Dan, but our result is that this conjecture is false. So we find a finite family of graphs, h1, h2, hm, and delta 1, delta 2, delta m density constraints, so that there are graphons that satisfy the density constraints, but no graphon that satisfies them is finitely forcible. So are there any questions about anything so far? Okay. So again, what this means is that the conjecture is false. So now let me give some brief overview of the proof. So this is kind of a picture. I'm definitely not going to go through this entire picture. So the basic idea is actually, even though we want something not finitely forcible, we kind of finitely force most of this structure so that it only varies in a very limited way, and then we can have a lot of control over where it varies, and that allows us to prevent any finite further set of constraints from fixing it. In particular, we force most of this structure, except there will be some densities here in C cross C and some densities here in C cross E that will vary. So the takeaway from here is that most of it will be constant. Most of the graphons in our set will look the same, except there will be a small limited part which will vary in a very controlled way. So to make that more precise, so we have our set of graphons, and they can be parametrized by a vector, an infinite dimensional vector z. So this z, the coordinates of z will in particular be densities of certain little squares, smaller and smaller squares in the graphon, but there will be other squares that kind of depend on them. But anyway, so the graphons in our set can be parametrized in this way, and we will kind of divide the coordinates of z into a set of coordinates of size 1, a set of coordinates of size 2, a set of coordinates of size 3, and so on, a set of coordinates of size n, and so on. So we kind of think of the z as z1, z2, zn, where these are not single coordinates, but zn is an n-dimensional vector. And then the way we've constructed the graphon, we have these functions fn of z, which gives, so we list all finite graphs, and then this function fn of z gives the density of the nth finite graph in wz. And then if we choose wz carefully, then each fn will be nice. So it can be approximated by a kind of infinite dimensional Taylor series. In particular, the later coordinates, since they affect the densities of smaller and smaller squares, they will have less and less of an effect on this. So the takeaway here is we have this set of graphons parametrized by this infinite dimensional coordinates, and the density of graphs of a graph Fn in WZ depends by a nice function of the z, is a nice function of the z's, as nice as an infinite dimensional function can be, I guess. So if we have these functions, so now we want to choose this set X so that it has the following property. If we fix kind of Z1, Z2, Zn, then we will have multiple extensions of this Z1, Z2, Zn to this infinite dimensional vector Z. But for any two such extensions, we want that Fn, the density of the nth graph, will be the same. And so let's say 2-sentence summary of a 20-page proof of why we can do this is the following. So if we've fixed Z1, Z2, Zn, then if we want to choose Zn plus 1, then we have n plus 1 degrees of freedom, because we're in 0, 1 to the n plus 1, and we have n functions that we want to fix. We want f1, f2, fn to stay constant. So we can kind of vary if we've chosen the set so far carefully, we can still keep 1 degree of freedom where we can vary Zn plus 1, and the density of the first n graphs will not be affected. So, and then because these functions are nice, we can define it by infinitely many polynomial equations which kind of approximate these functions, which have upper and lower bounds, and then we force that in the Graphon. So maybe I should just think through out loud why this works. So this then means that if we have this set of constraints, if you add any finite further set of constraints, that will only be affected by the first n functions for some n, and then we can fix since there's going to be some point which satisfies those constraints, there will be some z there will be some set of first n coordinates which satisfy them, and then there will be multiple extensions which will have the same values on the first n functions. So that's why this kind of gives a counterexample. And maybe I'll just return to this picture again, and I'll just say that we actually used the previous result by kind of forcing a subgraphon. So this is kind of the construction that Tyza mentioned in the previous talk, where we force a small square here that encodes the upper and lower bounds for our polynomial, and then we force a square to contain the values of our polynomial, and then we can kind of check whether the values are between the upper and lower bound. Okay, so that's all I'll say about the proof, but hopefully it gives a good general idea of the basic outline. So I'll say one more thing here. So for this Fn, it wasn't necessarily for them to actually be the density functions. We used that they're nice, which I didn't define precisely, but that's all we used about them. So in particular, Dan mentioned this entropy function, and we can actually add that to be one of the functions. And so this can give like a slight extension of our result where we have this finite set of constraints, and not only is any W that satisfies them not finitely forcible, but they all have the same non-zero entropy. And I'll finish there. Thank you for your attention.
Are there any questions?
Peter, is there some kind of Turing completeness type result that you can prove using these techniques?
So there was something, right? It's
So what exactly is the question?
Sorry?
What exactly is the question?
Well, I'm saying, can I program by asking extremal graph theory questions? Like, are these things as complicated as Turing machines?
Well, so they are, right? Because there is an early version of these results where you can kind of simulate a Turing machine in a Graphon. So that was kind of an earlier version, which I think Dan had talked about at a few places, and then so you can simulate, you can force a Turing machine within the Graphon. And
Any other questions? So, is there any hope of recovering a weaker version of the conjecture that you disproved, or is this the end of the deadline?
it's a good question. I mean, it's certainly a very convoluted, the extremal problem with no finitely forcible solution would certainly be a very convoluted extremal problem that is very different from ones that people actually study. But, so possibly you could say if it's simple, but I don't know.